Welcome back, everybody. What we're going to do today is focus on Chapter 4, Section 1. So we're essentially looking at Section 4.1. And we're going to focus on the mean, the median, and the mode. And what we did in the previous chapters was talk about how we can summarize our data using tables and graphs. And what we're going to do here is focus on summarizing our data using a few key numbers, specifically these measures of central tendency, the mean, the median, and the mode. So let's go ahead and jump right in. This table right here does a great job of describing each measure. For right now, I'll just introduce each measure, and then you'll see how the additional columns that I'm going to add in provide us with much more detail. And that's the level of detail that you'll understand after this presentation, and you'll want to come back and check out this table as you're studying because it does a really good job of talking about the key characteristics of each measure. So first of all, the mean is just the average that you've probably been computing since first grade. And it's just based on arithmetic. So we just sum up all the values and divide by the number of values. It's very easy. That's why it's our most familiar form of computing an average. It's very common. The median is common as well, not as common as the mean, but it's used very often. And that's because it does a great job of filling in for the mean when the mean has some trouble. And we're going to learn the mean has some trouble when we have outliers in our data. The median is simply the middle value, so it's kind of the geometric average. If the mean is the average based on arithmetic, the median is the average essentially based on geometry. Our mode is simply the most frequent value. It's very simplistic. We just look at our data set and figure out what value occurs more often than any other. Because it's so simplistic, it has some problems, and that's why it's not used nearly as often as the others. Here are some other characteristics of these measures of central tendency. You will understand them better as we go through the rest of the presentation. So we'll talk about these things as we go, but the table does a great job of putting it all together. So let's go ahead and explore each of these measures of central tendency. Let's start with an example. Let's say that we have some grocery stores in our area and they're all selling an energy bar, the same energy bar, and we're trying to figure out an average price so we can understand this particular item on the market. So we want to compute the mean, and the mean is simply based on the prices from these 8 stores. All right, so the solution to this is pretty simple. We're going to compute a simple sample mean. You might recall that a sample mean uses this symbol right here, X bar, as its symbol. And all we're going to do is sum up all the data and divide by the number of data points in that sample. So let's go ahead and do that. Let's first sum up the data. So we'll pull out our calculator. First value is 109. We'll add to that 129. We'll add to that $1.29 again. Then we have $1.35. We have $1.39. We're going to add $1.49 and $1.59 and then $1.79. And that gives us a grand total of $11.28. So our sum of x equals $11.28, and we're going to divide by the number of data points we have. 1, 2, 3, 4, 5, 6, 7, 8. Excuse me. 8. Okay, let's just do the division real quickly. So we have 11.28 divided by 8 equals $1.41. So we have $1.41. All right, well, that's our mean. It's really that easy to compute, obviously. So more important than computing it, let's make sure we understand its characteristics. The math in this section is not going to be difficult. What is more challenging is understanding what these measures are doing, what's good and what's bad. All right, here's something that's really good. The mean is mathematically derived, and what I mean by that is that we have a formula. You'll see we're not going to have a formula for either of the other measures of central tendency. Here's another thing that's really good. All values are used to compute the mean. So you see every single one of these values that we got from our data set had an equal say in computing this overall average. That's not necessarily going to be true with our other measures of central tendency. So because every single data point has its say in the final answer, the mean tends to be very representative of all of the data. So it's mathematically derived, it's representative. That's why it's essentially our default measure of central tendency. All things being equal, we really like the mean. Here are a couple drawbacks. This one's not such a big deal, but in order to compute a mean, we need at least interval level data. So interval or ratio level data. Because when we compute a mean, you see there's often a fractional component. Well, that fractional component is only going to make sense if we have equal intervals along the entire number line. And here's the main problem with the mean. It's very influenced by outliers. You might recall that an outlier is a data point that's very different from the rest of the data. So you can see most of these prices are relatively similar. There's not one value that's way out of whack. If there was, it would really affect our mean. We'll see that in the next example. So we're going to include an outlier. So here we've got some prices that are pretty similar. And let's say in our area there's an airport. And if you've been to the airport, you know that when you go to one of their stores to buy a snack, they're very expensive. Let's say the airport is charging $10 for this snack. Let's go ahead and compute the mean in this particular case. So again, we're going to use our same formula for computing the mean, sum of x divided by n. Let's go ahead and add up these values. So we have $1.09 plus $1.29 plus $1.29 again plus $1.35. To that we will add $1.39. We'll add $1.49, $1.59, and then finally $10. So that gives us a total there, the sum of x, equal to $19.49. So this would equal $19.49. And we want to divide by the number of data points, 1, 2, 3, 4, 5, 6, 7, 8. So divided by 8. Let's use our calculator again here. 1949 divided by 8 equals $2.44. $2.44. All right, now you can see that outlier, this value right here, it really inflated this mean. And do you see how the mean is no longer a good representative value of all the values in this distribution? I mean, most of these values are in the $1 range, and our mean here is between the $2 and the $3 range. It's not doing a good job now of capturing the bulk of the data. So although the mean is our default measure of central tendency, we're going to find that the median is typically more appropriate, and in this case that means more representative, when outliers exist. So let's go ahead and compute medians next. So let's look at our data again. So based on that energy bar data, let's compute the median. And you can see the median is essentially the average based on geometry, based on where the value is located. Another term for the median is the 50th percentile. It's the point at which half the scores are at or above it in value, and 50% of the scores are at or below it in value. So it's right there in the middle. Now, we have a little formula here for computing where the median is located. So this ML stands for the median's location. We do not have a formula for actually computing the value for the median. So make sure you understand that. That's one of the drawbacks of the median, really. Because it's not mathematically derived and there's no formula for it, it won't serve as the basis for more advanced statistical techniques. The mean will, the median will not. All this is a formula for finding the midpoint. I know it seems easy enough to find the midpoint, but this makes sure we can find it precisely, and in a large list of data, it makes things a lot easier. So here is all of our data. I've got it broken up just a little bit here in terms of the number of values so we can more easily see it. But in order to use this formula to find the median location, we're simply going to take our n, which equals 1, 2, 3, 4, 5, 6, 7, 8, and then divide by 2. I'm sorry, n plus 1. So we've got 8 plus 1 divided by 2. So in this case, we would have 9 divided by 2, which equals 4.5 or 4.5. And what that's telling us is that the median is located between the 4th and the 5th value. So here's our first value, our second value, our third value. There's the fourth value, and that's the fifth value. You can clearly see these are the middle values here. And I'm trying to tell you that the median is located between the fourth and the fifth value. So if it's located between those two values, we're going to want to compute an average of those two values to find the actual median. And the average between $1.35 and $1.39 would be $1.37. So 137. So we can see right in there is where the median is. That's that point at which half the scores are at or above it in price, half the scores are at or below it in price. The geometric average. So when we compute the median, it'll be a little bit more straightforward when our n, the number of data points, is odd, simply because we won't have to do any averaging in here. Let's go ahead and look at an example like that just to make sure we're understanding it. And in this case, what we're going to do is include an outlier too. So not only are you going to see how we compute the median when we have an odd number of cases, but you're also going to see the main benefit of using a median. So let's go ahead and find the solution. What we do here again is find our median location by using our formula. So we're going to figure out what our n is. We have 1, 2, 3, 4, 5, 6, 7 scores, 7 prices. 7 plus 1 divided by 2. 7 plus 1 equals 8. 8 divided by 2 equals 4. So our median is in the fourth location. Here's the first, here's the second, here's the third, here's the fourth. And we can check our work by counting from the other side. In fact, you should do that. We should have done it with the previous one as well. We can consider this the first score, the second score, the third score, there's the fourth score. So if we've counted right, we should find the center point no matter which side we start from. So here we see that the median is that middle value. In this case, it's doing a pretty good job of describing the majority of the data. And you can see that it's not influenced by this outlier because it's simply the middle value. It doesn't matter how extreme this value is. In fact, if that was not $10 but $110 for that energy bar, the median would still be the same. Imagine how much that extreme value would influence the mean. The mean that we compute would be very high, not representative of the majority of the data. So let's talk about what we like and some of the drawbacks of using a median. First of all, the main thing we like is that the median is not affected by outliers. That's a good thing. Here's another good thing. It can be used with ordinal, interval, or ratio data. So as long as we can take the data and order it from the lowest value to a highest value, we don't even need equal intervals. We can still find that middle value. Here are a couple points that are not as positive. First of all here, the median is not mathematically derived. So although I can show you a formula for finding the location of the midpoint, I can't give you a mathematical formula for finding the actual value that denotes that midpoint. And with that being the case, the median is not usually used for more advanced statistical procedures. Here's another thing that's not wonderful. Not all values are used to compute it. If you think about it, the median is simply that middle location. So although we look to see how many values we have to find that middle location, we're really just interested in this one value. So because all of the values don't have their say in figuring out what the median is, being that that's the case, it's not necessarily always as representative of the data as a mean. So again, just to kind of sum up, we like the mean. The mean is our basic measure. It's the default measure that we would use, everything being equal. But when we have outliers, we're probably going to want to use a median. Let's go ahead and talk about the mode. Here again, we have the prices of those energy bars. If we want to compute the modal value, it's just simply the most common value. So in this case, we can see that there are two stores selling this energy bar for $1.29, and I don't see any other values that repeat themselves. So in this case, 129 would be the modal value. It's the most typical value, essentially, that stores are selling this energy bar. Now, in this case, that doesn't necessarily make me feel so good because there are only two stores that we're selling this at 129 out of all the stores that we had listed here. And imagine if we had a huge data set. If we were looking at all the stores in the state that sell it, we might have, 500 different values. Imagine if just 2 had the same value and every other store was selling at some slightly different amount. You can see that that kind of leaves us wanting a little bit more. I'd hate to pick one value to summarize all the data when only 2 of them are the same. So this is one thing that makes the mode a little bit simplistic, particularly when we're dealing with unique values, and prices are sometimes like that. Someone might sell something for $1.29. Maybe they sell it for $1.26. There's not a big difference there, but the values aren't exactly the same. So the mode is just really a little bit too simplistic sometimes. But there are some good points, and one point is it's very easy to find it. You just find the most frequently occurring value, and it's very easy to understand. Another thing on its side is that we can find a mode with any type of data: nominal, ordinal, interval, or ratio. You might recall when we're dealing with nominal data, we're not even dealing with something numerical. We're just dealing with names of categories. So for example, if I were to ask you what brand of cell phone you plan to buy in the future, you're going to give me some names like iPhone or Samsung, and I can figure out which brand name was mentioned most frequently. That would be the modal response. So I can use it with any type of data, and that's really nice. Here are some of the points that are a little bit more negative. The mode is not mathematically derived. You can see there's no formula that we talked about for computing the mode. And that being the case, it won't be used for more advanced statistical procedures. Not all values are used to compute it. In fact, it doesn't even matter what any of these other values are. I just simply want to figure out what value occurs more frequently than others, in this case 129. So if all values are not used to compute it, the mode is probably not going to be in the long run as representative a measure of the center of the distribution as, for example, our mean would be. And here's another thing: there often is no mode. Let's say that these people were selling that energy bar not for $1.29, but like $1.26. Now you'd see in our data set, there's no score that occurs most frequently. There would be no mode. Let me give you a little example here that makes an important point. Let's say a teacher's class complained that their grades from the last exam were too low and that the teacher should curve them higher. You've probably heard some students in classes that you've been in previously asking for this type of request. Are you going to curve the grades? They're too low. They said it just doesn't seem right that the class average would be 65%. The teacher said that he would not adjust the grades because they are fine and the average is 80% correct, which is actually kind of high according to this particular professor. Can both sides be right? Now let's think about this for a second. The mean, the median, and the mode, when we compute those 3 measures on the same data set, we won't always get exactly the same values. So we can see here where it's possible that people can be talking about an average value, but talking about different values. Let me give you just an example. Let's say that these were scores on that last exam that the students were talking about. And let's say we wanted to compute a simple mean. Let's say we wanted to compute a simple mean. So compute x bar. And all we're going to do is add up all these values. So we're going to take the sum of x and divide by n. Let's go ahead and do that real quickly. Clear out our calculator. So there was a score of 10 plus another 10 plus 10 plus 50 plus 60 plus 70 plus 75 plus 80 plus another 80 plus 82, and then we'll add 84, we'll add 86, we'll add 88, we will add 94, and then finally to that we'll add 96, and that equals 975 points total. So you've got 975 is the sum of x, and we want to divide by n. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So we have 15 grades. Okay, so let's compute the mean here real quickly. 975 divided by 15 would give us an average score of 65. So the average score on the exam, 65. So we can see that's where the students were coming from. They're saying the average score is 65. That doesn't seem fair. Now, the instructor, though, came up with a value of 80 as being the average. We're using the term average kind of loosely. It's possible here that the instructor was thinking about the median. So let's find the median's location. That equals n plus 1 divided by 2. We saw that our n equals 15. 15 plus 1 equals 16. 16 divided by 2 equals 8. So the median is in the 8th position. We order our values from lowest to highest so that we can find the 8th position. There's the first, the second, the third, the fourth, the fifth, the sixth, the seventh. Here's the 8th. A score of 80. Let's check our work. Count from the other side. 1, 2, 3, 4, 5, 6, 7, 8. So in this case, we can see now where the professor was getting his point, that the average score was actually 80. So my point is that the mean, the median, and the mode, unless we have perfectly normally distributed data, will not all give us exactly the same value. And this is one way that sometimes people can play games with the data by selecting the measure of central tendency that suits them best. So just to kind of summarize real quickly, we have this table again. This table does a great job of talking about all the different properties of each measure of central tendency. So be sure that you can compute each measure, that's the easy thing, but also make sure that you can identify the strengths and the weaknesses of each measure, and they are summarized very well in this table. Let's talk about one more thing before we're done. Let's talk about weighted means. Weights give, it says here, relative importance to the data. When we were computing means before, we were giving each piece of data equal importance because we simply added all the data together and divided by the number of data points we had. Well, sometimes we're in some situations in which we'll already know an average value, like for a group, but we won't want to give each group equal weighting when we find an overall average. You'll see what I mean when we go through this example. So one thing that's true is that if we take our country and we split it up by the different time zones, so we have the Eastern time zone, Central time zone, Mountain time zone, and Pacific time zone, we don't have equal proportions of people living in all those time zones. About 50% of our population lives in our time zone right here. There are lots of people that live in this area. Another 30% live in this Central time zone. There are very few people who live in the Mountain time zone, about 5%. Then we've got about 15% that live in this Pacific time zone. Well, let's say we're looking at the average number of kids that people have in these different time zones. And let's say we already know that in this time zone, I'll just use some simple numbers to make things easy, that the average, and let's say we're looking at census data, the average number of kids per family is 2 in this time zone. Let's say in this time zone it equals 2.5. In this time zone it equals 6, which is quite large. Let's say that for whatever reason in this part of the country there are some families with some large numbers of kids, and then this 3. Now if I wanted to compute a weighted mean, I would need to take into account that there are so many people who live here, quite a few people who live here, very few people who live here, and then, some people that live here. I want these numbers to be weighted based on the number of people, the proportion of people who live in these areas. Because if I were to just simply add up these values and compute a mean, I'd be giving these people equal weight as these people, even though there's just 5% of the population here, but 10 times that number here. You see that point? Why would I want to simply average these 4 numbers when there are 10 times as many people in this area as there are in this area? Well, that's what a weighted mean is all about. So let's compute it really quickly. We'll just use WM to signify a weighted mean. And all we're going to do here is we're going to take the number of kids for the time zone and we're going to multiply it by its weight. So its weight is going to be the proportion of the overall population in this case. So we'll take 3 kids times 15. And we're going to add to that 6 kids multiplied by their weight. The weight for this particular area is 5%, so that's 6 times 5. I'm trying to put these in parentheses just to keep things neat. Let's look at the next time zone. We have 2.5 kids, 2.5 times the size of that time zone. Central time zone is 30%, so we're going to weight that with a value of 30, plus the number of kids in the next time zone, 2, multiplied by their weight. Well, that's 50% of our population, so we'll give them a weight of 50. So you can see that we gave each region weights, and then we multiplied those weights by the number of kids. Now all we need to do is divide by the sum of our weights. So take 15 plus 5 plus 30 plus 50. All right, let's simplify and solve that. Let's go ahead and work this out. 3 times 15, we could probably do most of this in our head, equals 45, plus 6 times 5 is 30, plus 2.5 times 30. Let's see, that's 60, that would be 75, plus 2 times 50, that equals 100. And then we're going to divide that by 15 and 5 is 20, plus 30 is 50, plus 50 is 100. Okay? So let's add this up. 45 and 30 is 75. 75 and 75 is 150, plus 100 would be 250. So we're left with 250 divided by 100. And 250 divided by 100, you can see that 100 is going to go in there 2.5 times, so it equals 2.5. So you can see here, the overall average makes sense based on our entire population, that the average number of kids per family equals 2.5. It makes sense, and it's also giving everything its appropriate weight. We see that this particular time zone got its heaviest weighting because most people live there. This particular time zone got the least heavy weighting because so few people live there, and the overall answer reflects that. You can see that this mean is much closer to 2 than it is to 6. That's what a weighted mean is all about. It's giving each particular number that we use when computing an average its relative importance, its appropriate weight. We'll do an example like that in class. That, my friends, was the key content from section 4.1. For now, that is all.